most people. So David Gross got a honorary PhD degree from our university in 2006. So we're very proud that David is our honorary alumni. So David is going to talk about fundamental physics.
Thank you. So it really is a great pleasure to be here for many reasons. The first, of course, is to celebrate the 5th anniversary of SAIFR ICTP, which I've followed and been involved with a very little for the last 5, even more, initial conversations with Nathan before then. And as Peter was saying this morning, for those of us who have some experience with institutes like this around the world, the progress that has been made here in just 5 years is truly remarkable. And I think many people seated here should take credit for that and deserve our thanks, as well as the state of São Paulo, whose contributions to science in Brazil we heard about this morning, which are truly remarkable. So I too am happy to congratulate this institute, and I expect great things from it in the future. It's also nice to be here, by the way, on this particular day, one day before my countrymen decide the fate of the world, the prospects of which are terrifying, and it's nice to have a diversion from...
Stay longer.
Sorry?
Stay longer.
I might have to. So, when I got here a few days ago, Nathan reminded me that he wanted me to talk again, twice, and he gave me a title, Fundamental Physics. Oops, how did I get there? Yes, Fundamental Physics, here it is. So I pieced together a talk, and I apologize to those members of the audience who will see more than once recycled slides from other talks. Fundamental physics, of course, can mean many things to many people. One of the nice things about current state of fundamental physics, at least from the theoretical side, is that it's all coming together, and I'll say something about that later. But of course, for me, fundamental physics really means particle physics. And we have this incredible theory called the Standard Model of Elementary Particle Physics that was formulated over 40 years ago and is a remarkable, successful description of the constituents of matter, all the matter in the universe that we have directly observed, and the forces that act within the atom and the nucleus. And this is truly a magnificent construction. And in a sense, fundamental physics consists of, at the moment, the well-tested and incredibly successful part of, consists of the standard theory of elementary particles together with classical general relativistic theory of gravity. And this framework, this theory, works from the Planck length, as far as we know, to the edge of the universe. So this is one of the great achievements of physics. But the challenges we face are trying to understand the parts of the observable universe that don't naturally, or we're not sure how we could fit them into this scheme, and those reconciling those parts of the general theory that don't fit together so well, and going beyond it. That includes understanding the mass content of the universe, including, most importantly, the observed dark matter that we observe gravitationally throughout the universe, and yet have not either detected nor produced. So perhaps the most glaring experimental challenge to the standard theory of fundamental physics is accounting for the mass and energy that we observe out there and whose nature we would like to understand and whose magnitude we would like to calculate. So this is a theory, the standard theory, I like to call it, not the standard model. It's the best theory physics has ever had. You can put it on a t-shirt and in principle, in a reductionist sense, calculate just about everything that we've ever measured. And many such calculations work very well. No discrepancies. But it contains elements, especially the Yukawa couplings of the Higgs particle, the Higgs meson 2, quarks and leptons that determine their masses and mixings that we don't understand at all. A lot of people are worried about very small numbers that appear in the hierarchical scheme of the standard model, but just the mass matrix of quarks and leptons contains many, many small numbers that we have no explanation for. And 40 years after the standard model and the theory of the forces of these particles has been worked out and tested and understood and used, we still have no clue, really. No experimental clue, many theoretical ideas, most of them haven't been very quantitatively successful for understanding this very strange mass spectrum, which is full of very large or small numbers. So these are issues that arise from the observation of dark matter, whose nature we need to understand, and the mystery of why many of the properties, many of the parameters that go into the standard model are what they are. That's a theoretical question, whereas the existence of dark matter is an experimental challenge. So what is the current situation of the standard model and particle physics? Well, here I think the bottleneck is experimental and not theoretical. Theorists have been working very hard for 40 years trying to understand some of these deep questions. There are many more that I haven't discussed, and they've come up with wonderful ideas and speculations, but what's really lacking is experimental evidence for discrepancies in the standard model or evidence for new physics. And the reason that that's the case is not the fault of our experimental friends who have been building impressive new instruments like the LHC and doing impressive experiments using impressive detectors and coming up with unbelievably beautiful results, extraordinary precision. The culprit here is nature. It's the existence of the Planck Scale, which Max Planck recognized over 100 years ago. That is the only obvious scale where new physics has to arise, and is awfully far off from present observation. Now, the Planck scale, as small as it is, 10 to the minus 33 centimeters, or 10 to the 19 billion electron volts of energy, is a very far off scale from current observation. But for us theorists, that's not a problem. And that's because we've learned that standard model physics varies logarithmically with energy. So as you increase by many factors of 10 the energy scale or distance scale you are studying, physics changes very slowly, like log of your scaling. And therefore, it's not so difficult for theorists to extrapolate by many, many orders of magnitude, way beyond anything that any sane person would think is safe. And that's why we were able, even way back in the 1970s, to scale up our understanding of the atomic and nuclear forces from where these forces were observed and measured and understood to extremely high energies. The variation here of the strength of the forces of the electromagnetic and weak and strong nuclear forces with energy or distance is very slow, logarithmic. So from a theoretical point of view, that's great. We can trust our extrapolation over many, many orders of magnitude, maybe even 15 orders of magnitude. And that not only gave the first, well, one of the quantitative first tests of clues that the forces, the atomic and subnuclear forces might unify if looked at very short distances, but also that happens near the Planck scale, which, as Planck discovered, is where gravity becomes important, and the quantum effects of gravity strong and unignorable. And that kind of extrapolation gave us a very strong clue, already in the 1970s, that the one clear threshold, the Planck scale, might be where unification of the forces together with gravity takes place in some way, and led to attempts to do that, culminating in the most successful of such attempts, namely string theory, so-called, the attempt to understand the basic particles as actually extended objects, which can unify all the forces of nature. That, to me, still represents the most important clue as to physics beyond the standard model, including gravity, that came from the standard model. It's an important clue for the unification of all the forces that we know about with gravity at this fundamental scale of physics, defined by Planck's constant, velocity of light, and Newton's constant. And a lot of the research in fundamental physics is the last 40 years has been based on taking this clue seriously and trying to achieve that goal of unification. But we must remember that it could be a coincidence. And some people are willing to throw this clue out as time goes on, or they want to change, introduce some new effect. And that's the nature of the game in fundamental physics. So on the theoretical side, that's very nice. But on the experimental side, extrapolating to higher energies or shorter distance scales rises quadratically, at least, with the energy. And so it's harder and harder to extrapolate experiments to shorter distances and higher energies. This is a fact of nature. There's nothing you can do about it. This is a discovery we made about nature. Physics changes logarithmically. The cost of doing, the difficulty of doing experiments changes like the square of the energy. And that's one of the reasons we're in this situation we are today, with theory extraordinarily successful, and yet we face a paucity of clues about what comes next and what's necessary to unify the forces or explain some of the mysteries of the standard model or the observed universe. It's what I call the cursive logarithms. Another way of showing this. Physics, S stands for physics, varies logarithmically with energy. So, the atom, we start with the atom, 100 years ago was explained by Rutherford in quantum mechanics, and we go to nuclear physics, the strong force. That's an extrapolation of 100,000. On a logarithmic scale, it's not so big. The weak scale is maybe a factor of 100 bigger. The LHC probes this scale nowadays, and we hope to build machines 10 times bigger. And gravity, the Planck Scale, is out here. So that this picture is reassuring. In 100 years, from knowing nothing about what atoms are or what they're made out of, we've gotten to understand atomic and nuclear physics, and it's only another 100 years perhaps to complete our understanding of the Planck Scale. Unfortunately, again, the dollars represents the effort to do the experiments, or the cost increases like energy squared, like the exponential of physics. And Fermilab, say, which explored the 1 TeV regime, is here, LHC is here, and if you want to know where, I'm not sure what direction is that, south, north? Does anybody know where we are? Anyway, let's assume it's north. Then New York is where you'd have to go to get to the Planck Scale. So that's not very good. However, as I said in my talk 2 days ago, we have to be encouraged by Einstein's encouragement, who said this attempt to derive the laws of nature, or at least us theorists have to be encouraged with, along a purely mental path. So sitting in institutes like this and trying to figure out the answer to some of the questions that are unanswered, encourages continuation in this speculative direction. Einstein, of course, had been very successful in doing that. The dangers of which everyone vividly must keep in sight who dares follow it. So we continue, and actually, in ways that I think have been extraordinarily productive and insightful, and have greatly enlarged our understanding of the framework of theoretical physics over the last 40 years. But the dangers of which is that we have only a few clues, one being the unification of the forces, and we have to take those seriously because we only have a few clues. And we must do everything we can to help our experimental friends give us more clues. So we must fully explore the next achievable range of energies that can be built. And in fact, were already built in Texas 40 years ago, well, 20 years ago. And so there are ideas around being pursued by our experimental colleagues of going farther, complementing the LHC, or going much farther to higher energies. 100 TeV is sort of the scale which one would like to get to, not just by extending the LHC with a 100-kilometer tunnel under Lake Geneva, which is being thought of, but bringing in a new player into the game, the largest economy in the world, which is now stepping up to serious major investment in fundamental basic science, basic experimental science, and theoretical. And this is the potential, the proposed site of an accelerator complex that would start with electron-positron collisions, but then go on to proton-proton collisions at 100 TeV. So, my opinion, no matter how you look at it, given the fact of nature that nature provides us with this disparity of scales, we have no option but to explore the next easily achievable energy scale. So let me turn to the way I view fundamental physics more broadly, theoretical fundamental physics, or fundamental theoretical physics. And perhaps the center of the excitement in my lifetime has been, and I'm not going to say string theory, rather quantum field theory. That is the basis of the framework of fundamental physics. It, of course, led to string theory, which was born as an attempt to understand the strong interactions and shares many of its features, and we now understand that in a deeper way, that to some extent, string theory, which grew out of an attempt to understand the flux tubes of QCD, is an alternate way of describing QCD. But string theory also connected and gave the first truly successful attempt, quantum mechanical treatment of quantum gravity, and then turned around string theory and started teaching us about both quantum field theory directly and many body theory, particular quantum critical points and quantum phases of matter. More recently, all of these fields have been shaken up by the realization that much of the understanding of states of quantum field theory, string theory, quantum gravity, phases of quantum matter all have to do with understanding better the nature of quantum states, quantum entanglement, quantum information. Finally, all of this has led to new understanding of, or new ideas about space-time itself. And all of these aspects of the increasingly unified framework of fundamental physics have an intimate connection with modern mathematical structures and geometry. So, fundamental physics, to a large extent, is becoming more and more unified. We just had a conference at the KITB, we have a program on symmetry-protected topological phases of matter, and there was a conference, and which was an incredibly intense and exciting conference with dozens and dozens of brilliant young condensed matter theorists who were using mathematics, cohomology of modular tensor categories, mathematics that wasn't even invented when I was a graduate student. And on the other hand, we had mathematicians and theoretical physicists like Dan Freed and Nadi Seibert talking about topological insulators and quantum computing. I mean, it's just remarkable the interplay of all these different aspects of, well, the one unifying feature, except for the mathematics, might be quantum. All of this is quantum physics. But it's getting sillier and sillier to distinguish at the level of this kind of fundamental physics between people doing condensed matter physics or string theory, QCD, quantum field theory. Quite a remarkable development. Fundamental physics is alive and vigorous and healthy as I've ever seen it. Now, I'm often asked, what do you think about string theory? Now that you haven't managed to do what you promised to do 30 years ago. And so the first thing I try to explain to them is that string theory isn't a theory. Some of these elements here are called theories. And so I've been pushing them recently, the idea that we should be a little more precise when we talk about, in fundamental physics, about frameworks, theories, and models. So let me explain what I mean. A framework is something like quantum mechanics or classical mechanics, or quantum field theory, which is called a theory, or string theory, which is called a theory. All of these are frameworks. There are many quantum field theories. There are also many string theories. And you might say, well, string theory always had the advantage that it didn't have parameters you could adjust. Everything was dynamical, so there's only one theory. But at least the way we construct string theories is by perturbatively expanding around some classical background, some classical state, semi-classical state. And there are many ways of doing that, and there are really many string theories. A framework like classical mechanics, quantum field theory / string theory are frameworks. Within those frameworks, you construct theories. So theories are something like Newton's theory of gravity, Einstein's theory of gravity, Maxwell's theory of electromagnetism, and the Standard Model, which for some historically bizarre reason, which I know, is called a model. It's not a model, it's a theory. So definite Lagrangian equations, a few parameters, it's a theory. Makes predictions. You can make very few predictions from a framework. There are ways of testing some of the so-called axioms of quantum field theory, but nobody does that. You test the theory. These theories are all well tested and disprovable. Very hard to disprove a framework. People for years have been trying to, for some reason that totally escapes me, disprove quantum mechanics. But that's difficult. You can disprove a theory. A model is a bit different. BCS theory, again, misuse of superconductivity, is a model of superconductivity. If it hadn't worked like some of the other models of superconductivity that people invented, you would change it a bit, but you wouldn't change the theory of condensed matter physics, which is roughly based on E&M and quantum mechanics. It's not going to change soon, if ever, is quantum mechanics. Within quantum mechanics, there is a relativistic quantum mechanics, quantum field theory, which is not really a theory, but a framework. There are many quantum field theories, a landscape of quantum field theories, infinite number of quantum field theories. Anyway, with a guide of experiment and intuition, we pick out the standard model, which is not a model, it's really a theory. A consistent quantum field theory, and then we can make predictions and test it, and it's passed just about all the tests we can perform. So when you have a theory, let's take my favorite, QCD, you can actually make predictions and test them now with LHC data with extraordinary accuracy. And any discrepancy that survives means that the theory must be modified or thrown out. You could also use a theory to calculate things with, in principle, arbitrary accuracy. That's the standard of physics. So, the framework currently of theoretical physics is quantum field theory. Now, it used to be thought that we had this other new framework, or new theory, called string theory. But what's been realized in the last 2 decades, more and more, is that these frameworks are really the same framework. And the remarkably rich and important understanding of duality, and Juan Maldacina's ADS-CFT duality is the best example of that, of these two, of describing the same physics by using different dual descriptions within the same framework has truly revolutionized both our idea of string theory. It's not really that revolutionary. And of quantum field theory, it's much richer than we previously thought, and has that richness gives us increased power to describe physics using different dual descriptions. The standard model, or the standard theory, is a particular theory within this framework, incomplete as it is. So, this framework that we now understand is much larger than just quantum field framework or string framework. Includes both particles and fields, strings and branes, all consistent field theories, probably, in quantum gravity. What is left out is a particular theory. What is left out is understanding, for example, how those forces that appear so different in the standard model are unified, and as I said, picking out a particular theory of the framework. The problem, you might say, of uniqueness. There are an infinite number of potential standard models. Why do we have the one we have? Why are the parameters that define that standard theory what they are, etc.? What picks the theory from the framework? That's a hard question. But if you try to understand the quark-lepton mass spectrum, you're in a sense asking that question. What picks up that version of the standard model with those particular masses from all possible masses? Now, I believe that this question that faces particle physics is related to 2 other questions, which really have to do with cosmology on the one hand and quantum gravity on the other. One is the beginning and end of time. So we have this incredible, also 100 years of understanding of the structure of the universe and its history, which has within 100 years gone unbelievably far back in the past and has given us a quantitative description of the complete history of the universe till now, except for the Big Bang, which is more and more a subject that is hard to avoid, since events or physics near the Big Bang, or near the beginning, or the singularity, if you extrapolate backwards, are potentially measurable in the cosmic microwave background and in the developmental structure. So, it is no longer religion or philosophy, it's physics, to at least address the question, how did the universe begin, and what is the initial condition? Ever since Einstein explained that the universe is the history of space-time, we are faced with this problem and can't avoid it. So, for a long time we can avoid it, but conceptually, there's no way to avoid it once space-time itself is dynamical. And now with our understanding of cosmology back to a very early time, it's becoming even potentially an observational question. We can no longer avoid asking what happened at the beginning, the boundary, or the end of space-time. And here, this is truly a new question, just like the question of uniqueness. What picks out a particular theory from all theories in the framework is not a question physicists usually worried about. You get one that works, that's fine. Here we ignored this question for centuries because we're really interested in telling experimenters what happens if they prepare something now and measure it a bit later. But when you're talking about the history of space-time, if you had the answer, it would contain a description of the beginning and the end, and what are the rules? And we have no idea because never had to ask that question before. So these two questions that we've never had to ask before, I think, might even be related. What picks out our universe? What picks out our theory? Potentially are connected. And finally, here we're talking about space-time. And we know how problematic our understanding of space-time gets when we start thinking about quantum space-time, quantum dynamics of space-time. So, the nature of space-time has become, especially in the context of the string framework approach, a more and more central issue, one which surely is related to this issue as well as this one. And here, the duality between the quantum field framework and the string framework has taught us a lot about how to think about space-time, because in that framework, one has these dual descriptions of physics, either in the most famous example of dynamics in a larger dimensional space, say anti-de Sitter space, and quantum states on a rigid boundary, which in this case is just flat space. And this has been the most fruitful example where one can probe the structure of space-time, the dynamics of space-time, Einstein's gravity, in terms of detailed properties of the quantum states that give the dual description of the boundary. And it's here where some of the most fruitful interactions have grown up and continue and deepen between physicists who are interested in properties of quantum states on the boundary, like condensed matter physicists who might be interested in critical points, quantum critical points, and gravitational or quantum gravitational or string theorists who are interested in strings or gravitons propagating in the bulk. And both sides are benefiting enormously from the profound dualities that relate these different descriptions. This is an example of emergent space, and it's one of the most explicit and currently fruitful ways of trying to understand whether space-time is best thought of as an emergent property, or an emergent concept in physics, whether there isn't something, a better way of describing physics. Of course, gravity, the dynamics of space-time, is then also emergent. But this again raises a kind of question that is totally novel. How do you formulate the rules of physics without space-time, especially without time? And we don't know. So, I'm going to leave a bit of time for another more philosophical ending. We have a wonderful theory of elementary particles, but the questions we ask that are unanswered are as exciting as they've ever been. We have fantastic instruments currently, and experiments going on, and experiments being planned, and instruments being planned. And we have fantastic speculations. So there's no question that the best is yet to come. Not just for physics, not just for fundamental physics, not just for theoretical physics, but also for, say, for ICTP. So congratulations. Now you might have noticed that I'm finishing ahead of time. So I'm going to add a little thing which I give often in public talks, but you might find enjoyable. And that is, oops, it's not that. Yeah. Extra. Like that is. Okay, I just want to briefly address, this was a pretty highfalutin talk. I talked about very fundamental questions, almost impossible to imagine answering. So this is a theorist game. Can we really continue doing this kind of game forever? So I want to address 3 points. One is, which was asked to me in the public lecture I gave 2 days ago. Okay, are you going to end up with a final theory and then, no more work? So let me discuss that a bit. And then, second question is, these are pretty hard questions. We're now faced with having to at least ask, how did the universe begin? Is this something we're smart enough to answer? And then, of course, we may lose the will to proceed. So let me discuss this question of a final theory, which people playing this kind of game, fundamental physics, are sometimes asked. Or they sometimes claim they have. Now, I'd like to turn this into a question like we do often now in physics, a question of geometry. So, I think this is a question having to do with the geometry of knowledge, and I want to construct a geometrical model of knowledge. There is, of course, the onion model, what I call the onion model. You peel away the layers of ignorance, you get to the core of the issue. That's the answer. But this model brings tears to my eyes. It explains nothing. It's not very elegant. Better model is that knowledge is a sphere of understanding, quantitative understanding, pushing out into a sea of ignorance. So it's inside out, an inverted onion. And so, just crudely speaking, this model explains a fact that we all experience in life. As knowledge increases, knowledge is sort of the volume of the sphere. Much of it's in libraries, but you can access it, Google it immediately nowadays. Ignorance is on the boundary of the sphere of knowledge. Ignorance out here is unknowable. So like Rumsfeld said, questions here are known unknowns, but questions out here are unknown unknowns, and who knows where they are. So ignorance really only increases like the surface. So this is a nice model because it explains something you learn at some point in your life. The more you know, the more you don't know, but you get wiser because knowledge increases faster than ignorance. But they both increase. So this model explains something you might not have thought of. Why does ignorance increase? So now, is there a final theory? Is the question about the global structure of the geometry of knowledge, because if there was a final theory, there would be no more ignorance. So for there to be a final theory, there has to be a finite amount of ignorance. Now this has happened before in some scientific fields, like the exploration of Earth. Well, this is a map from a Eurocentric map from the Middle Ages, showing the known Earth, the sphere of knowledge, and what one was ignorant of. By the way, you see there was no map of the unknown Americas. They were unknown. Unknown. Now here, we're scientific societies devoted to exploration of the Earth, and they carried out scientific expeditions. And if the Earth was flat, as some thought, this would have gone on forever. But the Earth isn't flat. It's round, compact, finite surface area. Eventually, one ran out of ignorance of unknown parts of the Earth, and at least with a resolution of a kilometer or maybe 100 meters, there's a final map of the Earth. And explorer societies have gone out of business. And explorer institutes have shut down. So the question is the sea of ignorance compact? Could be that it's unbounded and infinite, like the flat Earth, or a hyperbolic geometry, but it could be compact and finite. And eventually we'll run out of ignorance and have a final theory of physics. I don't know. I'm totally agnostic. The only thing I'm sure of is that there's no sign of curvature at the moment. we don't see a horizon. Every time we learn something, more and more questions arise. It still looks flat. But who knows? It looked flat for a long time to those medieval Europeans. This, of course, wouldn't be the end of physics, by the way. Most of physics is not reductionist fundamental physics that I've been talking about, but rather exploring the infinite variety of phenomena that can be, that exist in the real world. So that'll go on. But this fundamental physics, in the reductionist sense, could end or could not. At the moment, there's no danger of it ending. And your institute has a long time to survive. But maybe we're just too dumb. Maybe these questions are getting too profound. And why should our species, after only 100,000 years, be so arrogant to assume that, we're the pinnacle of evolution and we're smart enough to answer how the universe began and what is space-time really. We know that other species, our other friends, are too dumb to answer these questions. And have not been able to teach my dog quantum mechanics. And I understand that my dog can never understand quantum mechanics, no matter how I try. So why should we think that we are not in the same position and that we're nearing the point where we're just not going to be able to understand it or make progress? Did we evolve to understand quantum mechanics? Obviously we did somehow. But to ask how the universe began, maybe not. Here I'm optimistic because we possess, in fact, almost by definition, what Homo sapiens possess, the one thing that's different is language, whose highest form is mathematics, and that has infinite capacity. Noam Chomsky, the great linguist, once said that an infant who picks up a language somehow hardwired capability, listening to his parents, picks up a language, a human language, any language, and can then, all on his own, or her own, can utter sentences that have never been uttered before. So that's the infinite capacity of language and mathematics. So infinity is good. There are many infinities, however. This might not be infinite enough to understand some of the things we're faced with. But I appeal now to experimental evidence. Evidence that there's no sign that we are faced with questions so far that cannot be answered. So I think that if we were getting to that situation of the dog, it would take longer and longer for young theoretical physicists or young scientists to arrive at the frontiers of knowledge. It would get harder and harder and harder. We'd be up against the wall. Eventually, the students would die before they got their PhD. That's not happening. The brilliant young scientists who are attracted to theoretical physics nowadays are just as brilliant as they've ever been, and they start contributing to expanding knowledge as soon or as young as they've ever been. So if PhD, the time in which one got a PhD began to approach 60, 70 years, then we should begin to get worried. Even if that happened, we could start tinkering with our own brains. I'm not worried. I think the real problem that we face is not running out of ignorance or running out of mental capability, but losing the will of our friends, fellow citizens, build these incredibly expensive instruments and probe signals from the early universe or from very short distance physics. And here, I simply hope not. And I end this discussion with Hilbert's famous quote, "We must know, we will know." And now I've lived up to my reputation and ran over it. So thank you.
So I guess we can go forever, but unfortunately the talk cannot go forever. So thank you very much for this increasing our knowledge and ignorance. And we were running late, so David will be around for coffee break, and I can ask questions from him during coffee break. Okay? So let's thank David again for